Hey everyone, welcome to This Explainer. I am absolutely thrilled to have you here today. Look, if you're joining me, you probably already know the deal. In the world of maternity nursing, the stakes simply couldn't be higher. When you're managing a Pitocin or Oxytocin IV drip, your dosage calculations aren't just numbers on a page. They are literally dictating both a mother's contractions and a baby's heart rate. There is absolutely zero room for guesswork on the floor. So today, we're going to eliminate that guesswork entirely by completely mastering the desired over-have method for Pitocin calculations. Let's get into it. Okay, let's dive into this. We've got a 4-step plan today, starting with the math foundation, moving to calculating mLs per hour, then flipping it to calculate milliunits per minute, and finally navigating those tricky titration parameters. All right, section 1, the math foundation. We're talking about the golden metric conversion. Before we even think about touching a formula, we have to cement one absolute core rule directly into our memory banks. 1 unit is exactly equal to 1,000 milliunits. Why is this such a huge deal? Well, out in the real world, the doctor is almost always going to order Pitocin in milliunits per minute, right? But the pharmacy is going to hand you an IV bag that's measured in units. You've got to bridge that gap. Having this conversion locked in your head will make absolutely everything else we do today super easy. So let's break down the desired over have formula itself. This is basically our master key for solving these problems, and it's a beautifully simple structure. Step 1, grab your desired dose. That's what the patient actually needs. Step 2, divide it by your have dose, which is the amount sitting right there in your supply bag. And finally, step 3, just multiply that result by your quantity, meaning your total fluid volume. Desired divided by have times quantity. Simple, right? Moving right along to section 2, scenario 1, calculating ml per hour. Picture this. You've got a patient who needs to receive Pitocin at 6 milliunits per minute. We just need to extract the right data and plug it into our formula variables. Your desired dose? That's 6 milliunits per minute. You check your supply bag and it reads 10 units. So boom, there's your half dose. And that medication is all mixed up into 1,000 mLs of lactated Ringer solution, making 1,000 ml our quantity. But hang on a second, before you go rushing to divide those numbers, you have to watch out for a really common pitfall here. Notice the measurements we're dealing with, milliunits versus units. We've got a mismatch. You absolutely cannot divide these until they match. They have to be speaking the exact same language. So, how do we fix it? We do a little converting. A great rule of thumb is that going from a tiny measurement, like milliunits, to a larger measurement, like units, requires division. We simply take our 6 milliunits and divide it by that golden memory bank number of 1,000. That gives us 0.006 units. And just like that, our desired dose matches the units in our supply bag perfectly. Okay, let's bring it home and walk through the final math. We take our shiny new matching desired dose of 0.006, divide it by our supply of 10 units, and then multiply by our 1,000 ml volume. This spits out 0.6 mLs per minute. But remember, IV pumps don't run on minutes, they run on hours. So we just multiply that 0.6 by 60 minutes. That brings us to our final, safe, hour-based pump rate of 36 mLs per hour. You nailed it. All right, let's keep the momentum going. Section 3, Scenario 2, calculating milliunits per minute. Let's completely flip the script. Imagine you're taking over a shift, you glance at an IV pump, and it's currently running at 12 milliliters per hour. The provider walks up and wants to know the exact dose in milliunits per minute. Don't panic. Once again, we just map out the variables. Our desired dose we're working backwards from is 12 milliliters per hour. The bag hanging there is 1,000 milliliters, so that's our half dose, and the quantity of medication in that bag is 20 units. The great news here is that our units of measurement for that first division step perfectly match up as milliliters. We can safely divide 12 by 1,000 without a problem. However, before we solve the whole thing, notice where we need to end up. Our final answer needs to be in milliunits, but our quantity is sitting there as 20 units. We need to tap into the memory bank once more to convert those 20 units into milliunits before finishing the formula. Remember, going for a large measurement to a small one means we multiply. So, 20 units multiplied by 1,000 equals 20,000 milliunits. Now we can cruise right through the rest of the formula. 12 milliliters divided by 1,000 milliliters equals 0.012. Multiply that by our newly converted 20,000 millunits, and we get 240 millunits per hour. Now, the absolute kicker here is that the problem isn't asking for hours, it wants minutes. We just have to take one extra simple step to divide that 240 by 60 minutes, and there it is. The patient is receiving exactly 4 milliunits per minute. Moving into the homestretch, Section 4, Scenario 3, Navigating Titration Parameters. Now for the final act. We are stepping into a chaotic, real-world titration scenario. This is going to test your ability to filter out the noise. Think about all the distracting numbers getting thrown at the nurse here based on the provider's parameters. The drip started at 2 milliunits per minute. You're supposed to increase it by 2 milliunits every 30 minutes. The absolute max dose is 10 milliunits. After assessing mom and baby, you've successfully increased the current rate to 4 milliunits per minute. Oh, and your supply bag reads 30 units and 500 ml of normal saline. I mean, wow, that is just a ton of numbers. To survive this kind of information overload, we conceptually need to just cross out the distractions. The starting dose, the max dose, they just don't matter for programming the pump right at this exact moment. Let's isolate the vital data. Your newly increased titration rate of 4 milliunits per minute, that is your desired dose. And your supply bag of 30 units and 500 milliliters, those are your have and quantity values. Ah, much better. Just like in Scenario 1, we do a quick review and spot that familiar mismatch rule. Our desired dose is in milliunits, and our supply is in units. No problem, we just divide the 4 milliunits by our golden number 1,000, which gives us 0.004 units. Now it perfectly matches the 30 units in our supply bag. We are officially ready to plug it all in to our calculator. But wait, whatever you do, do not clear out your calculator. Seriously, I say this with extreme urgency because it is a massive trap for so many nurses. When you divide 0.004 by 30, your calculator is going to spit out a huge, messy repeating decimal, something like 0.0001333 to infinity. If you clear the calculator early to simplify things, or if you try to round it right now, you will absolutely ruin the final calculation and get the wrong pump rate. Instead, trust the process and keep that huge number on your screen. Multiply that exact repeating decimal by the 500 milliliter quantity. You'll get another repeating decimal, 0.0666. Just leave it there. Finally, multiply it by 60 to convert from minutes to hours. And just watch the magic happen. It beautifully, perfectly rounds out to a safe, whole number pump rate of exactly 4 milliliters per hour. How satisfying is that? So, I want to conclude with this somewhat provocative thought. In the delivery room, your math literally dictates 2 lives. Are your calculations ready for the real world? By leaning into this structured, methodical approach we just went over, you can filter out all that chaos, protect your patients, and do your job with absolute confidence. I strongly encourage you to seek out some practice quizzes to really cement this Pitocin math into your brain. Thank you so much for hanging out and exploring this with me today. Keep practicing those conversions, and I will catch you in the next explainer.